You tell me when I can
Okay,
start.
okay, I will go live. One moment. Okay, we are live.
Let me see. It's starting. Right. Hello, everybody, and thank you very much for joining tonight to the meetup, the March meetup of Data Science Milan. Tonight, we're going to talk about what data scientists should learn from quants. Before we jump into the technical talk, let's give you a brief introduction to our community. We are an independent group that was founded on February in 2016. We are a technical community counting more than 1.7 thousand members, and we meet up once a month. We are part of a larger association called the Italian Association for Machine Learning that supports us in our events. The staff is made of the people you see in this slide. Those are the guys that they make all of those events to happen. If you want to know more about what we do as a staff, or you would like to uh, be part of it, then you can reach us to datasciencemilan@gmail.com. And we're always looking for more volunteers to come on board. And in particular, at the moment, we're looking for a social media manager who can help with our uh, social media accounts as well as the contents on our website. Regarding the next events, we have one event scheduled for April, which is going to be about how to do machine learning on AWS. We'll talk about SageMaker and also other services, so stay tuned. If you want to know information about the everything we do and all the links and references to the previous events, that you can find everything on our website www.datasciencemilan.org. You will find the recordings, the slides of the previous talks. You can find the links to our Medium blog, where you can find a summary, the articles of each event. You can also, through the website, there is a section where you can register to the monthly digest. So Riccardo is our newsletter manager. He will select only the relevant events, the relevant articles, and the news from the community once a month, and will send to you to your inbox. If you want to keep in touch with the other community members, so if you want to ask questions about data science, machine learning, because you're looking for feedbacks from the community, or you want to share some article, any news with the rest of the community, you can go on, we can join our Slack channel. You can request an invitation through the datasciencemilan.org website. Just scroll at the bottom. There is a link you can use for asking the automated bot to send you an invite. All right. So if you also want to send your proposal for a talk, this is our email address. And let me give you a few updates from the community. There is an opening right now at the Limited Bank. It's a data scientist role in Milan. There is a data engineer opening at Qubit. It is based in Milan, but it is also considering remote opportunity. Covio is also expanding their team, looking for a data engineer. Again, it's either based in Milan or it can also be a remote position. Brainly, this is the company I work for. It's expanding with a lot of roles at the moment. There is a lead and senior data scientist roles, machine learning engineers with a specialization in natural language processing, information retrieval engineer, MLOps engineers. And again, this is not based in Milan. It's a company based in Krakow, but they have offices also in Barcelona, or you can work for Brainly remotely. Okay, now let's have a quick overview of the next upcoming conferences. There is a Code Motion in just a few days next week. There is the AI Summit on March the 30th and the 1st of April. So again, 10 days from now, and this event is very close. If you want to register now. There is the Global Summit for Python for Machine Learning and AI, which is the beginning of April. And there is the European chapter of the Association for Computational Linguistic conference that will take place online, I guess, between the 19th and the 23rd of April. Again, if you want us to post any message to this warbird to one of the next meetup, then just send us your correspondence. We can also publish it in the newsletter. All right, so the agenda for today is we have Alexander, who is the co-founder and machine learning director of Neurons Lab. But before we start with the talk, I have just one last thing I need to ask you, is that we need your support. We are a nonprofit association, and we do all of this because we are very passionate about spreading the knowledge about data science and machine learning. In exchange, what we ask you is simply to spread the word. So those are our Twitter, Facebook, YouTube, LinkedIn accounts. Please write about us, mention us, post some picture, try to expand our network through your contacts. Thank you very much and enjoy the rest of the event.
Gian Mario, thank you for the intro. Great, as always. And thanks everyone who came today, this Thursday evening. I mean, I know there's so many things to do online these days, right? Because everyone is fighting for your attention. And they also use machine learning algorithms to fight for your attention. But here we are. So I hope this will be your attention and my attention, our attention spent worth. You guys can, Gian Mario, you can see my screen, right? Everything's okay.
We do see your screen, even if it's not full screen. Now it is full screen.
Okay, perfect. Then we are all set. Yeah, basically today I wanted to give you a couple of, I hope, interesting insights. Some of them are technical, some of them are a bit more business related. But basically, I wanted to show a bit different perspective on a classic data science job. And I hope it will help you to rethink some of the processes from the perspective of the people who are really, really, really crazy about the risks, the performance. And I think we definitely have something to learn from them. And a couple of words about me. Today, I'm a consulting firm co-founder, Neurons Lab, and I'm responsible for the overall machine learning expertise, strategy, and development. Before, I was doing mainly two things. I was independent AI consultant in medical diagnostics and financial risk management. Basically, that's where my love for the quantitative finance and risk mitigation in different areas coming from. Basically, I was mainly working on the things where a single machine learning mistake can cost a lot in terms of human lives or financial losses. And this will pretty affect my speech today. And I used to teach in a couple of universities, University of Verona, Ukrainian Catholic University. I gave a small course in Kiev Polytechnic University. I don't do this anymore, but I still write some articles on Medium. So it's like X, not X educator, still coming back to this. And also what you should know, I am a really well self-critical person. I am thinking about risks maybe even too much. That's why very often you can see my face like on the right, thinking about all the great mistakes I did in my life. And today we will be discussing the difference between two worlds, the blue and the red pill, the world of something that looks like chaotic observations, basically financial markets, and the world of something that looks pretty stable and deterministic, basically pictures, texts, sounds, tabular data. Basically, this is the data that most of the data scientists use to and still work with. And I want to show you the story of how actually people from the left wanted to use the algorithms from the right, basically all these fancy machine learning algorithms. But at the end, I think that people from the left side, from the finance side, have a lot of things to teach people who are being on the right side with all this deep learning, etc., etc. And first of all, why people in finance decided to use machine learning at all? Because they have all their stochastic models, fancy statistics, knowledge of the markets, right? It's like maybe there is no need for machine learning. There are three kind of like high-level reasons. The relationship in finance are usually non-linear. They kind of jump, threshold, hierarchical. So the classic statistics, linear regressions are not really fit for the today's data. And today's data in finance is high dimensional. Basically, for a single event of the market, you might have so many variables. The number of samples is really low, meaning that if you want to have one more year of data in finance, you need to literally wait for 1 year. But if you want to have more pictures of the faces or more spam messages, you just go and collect it. You don't need to wait. And the structure is really, really weak because there are financial reports, there are news, there are Reddit channels, there are data from the airs, like alternative data, news. So there's really nothing like a structure. And the last, and I think this is a bit more focus of what we're going to talk today, that mathematical models in finance are designed to explain in sample patterns. So it's like we observe some financial situation, we build a mathematical model to explain it, and we say, wow, we created new stochastic differential equation, very cool. But what it has to do with doing something in the future? And machine learning supposedly can solve it all, right? Because deep learning is not linear, it deals pretty well with complex high-dimensional data, and when you fit a model, you basically validate on the test data, so you kind of automatically design whole your machine learning pipeline to work well on the out of sample. So machine learning looked like a salvation for the financial world, but in reality it is not. And because financial machine learning is actually not like using machine learning with financial data. And there are many lessons what people in finance learned, and I'll focus on just a couple of them in this talk. You will start adopting that is the cat picture of the cat will always stay the picture of the cat in the future, which will affect your machine learning design. Regarding the outputs, what you want to predict, I want to show you an approach at least kind of a bit more to the business first modeling than accuracy first modeling. I want to show you a couple of things regarding to the models that I hope will make deep learning uncool again, at least for some of you. I will talk a bit about the metrics that focus more on the confidence and reliability in the future than accuracy on some test set. Then I'll discuss a bit train set overfitting, and I'll show you that your favorite k-fold is, okay, maybe not dead, but barely breathing. And I wanted to introduce you something like a test set overfitting, which usually is not even discussed in data science literature, but it actually exists and it's really crucial. Let's start with the inputs. Basically, in finance, the classical examples of the data are those time series. And if you are not a finance professional, when you look on this Bloomberg terminal, some prices, they will look all the same to you. Basically, they'll look like these stochastic movements and you can try to predict them. And if you try to zoom each of these different lines, there can be a point in the point like today, the price is 1,000. And if you try to put this 1,000 into a machine learning model, this 1,000 price of a share today will not mean the same over time in the future, right? Because for different assets, for different situations, this 1,000 can mean completely different things. And it can be one problem because we can always normalize the data, right? You can say, I can use some kind of normalization. I can normalize this price of 1,000, the rest will be okay. The problem is that the nature of the data is coming from stochasticity with different degrees of freedom. And these three graphs that may look the same if you run so many samples, they come from three completely different simulations of three completely different stochastic processes. There is like a geometric Brownian motion, jump diffusion model, and the mean reverting model. And if you try to put it even normalized into machine learning model, you'll fail because what you have in the past of the stochastic simulations or some stochastic realizations from the market, it doesn't mean that the situation in the future will repeat. Because all these parameters, all this mu, sigma, s, y, etc., j, r, they will change in the future. There is no chance that the data set you have now over 10, 20 years will repeat itself. And basically, that's why these inputs have such a low signal to noise ratio that And there are invented many tricks to deal with this. I'm not going to talk about some specific financial tricks, but the idea is that what you have today in the data doesn't give you any promises it will stay tomorrow or in any point in the future the same. Any pattern you found today might disappear in the future. And in normal data science with picture, we actually also encounter the situation much more often than it looks like. There are two concepts that I think most of you guys saw, at least in some courses, maybe even in practice. One of them is covariate shift. Basically, that there are so many different cats in the distribution of the cats, so many different dogs, and this shift in the among the cats and the dogs can be so many different. And if you train on the cats of one breed, dogs of one breed in one situation, with one kind of camera, it doesn't mean that it will work with another breeds, with drone cats, drone dogs, etc., etc. And second, the interesting case is the concept shift. Basically, on the map on the right, you can see that the people in United States, they call the same Coca-Cola differently. They call it pop, they call it soda, they call it Coke. And if you train a model for text recognition, this model simply will work differently in different states. And this is something what we usually, at least kind of in the basic pipelines, we don't really consider. But it reminds like what happens in finance. The same thing will not mean the same in the future. And it happens in the medical diagnostics. It happens in the self-driving cars because the geography, the weather can change. It happened with the retail at COVID. I think when you went in the like 1 year ago, when you went to do the groceries and you saw like that the floor and some elementaries are disappearing, they're not present simply in the supermarket. It means that their forecasting model didn't work in a new situation, and they couldn't do nothing because all they know how to do is just to fit predict, and this prediction didn't work anymore. More the spam filters, because the people who send the spam, they evolve over time, and the spam model that was trained on data yesterday will not mean the same in the future. Advertising, recommender system, face detectors with the mask. There are many different examples, and the idea I want to tell you with this first thing is that forget about the data sets, because the real life is not a data set. Real life is the environment that is constantly changing, just like the markets. And all what you have is a sample from the environment during this period of time. And if you start rethinking your data sets as small samples from the environment, you'll come to a different kind of modeling. Okay, this is the inputs. What happens with the outputs? In finance, people usually don't really predict the price. Even if some people try to predict the price, it's really wrong approach. The most successful approach to predicting modeling in finance is actually to predict the trade and the limits of the trade, the exact take profit, stop loss. So basically what you predict is not the like stochastic process and the price and stochastic process. You want to predict the outcome of your investment decision. And this is a big difference because as you see in this kind of red graphs here, basically investment decision has some lower bound, upper bound, it has some length of the decision, has some limits, and that's what you actually want to model. But when we talk about classic data science, basically we just predict a number or we predict a category. And how we can move from the number or a category to actually a financial decision, just like we do in finance. This sounds what is a bit less trivial, but if you look on the picture on the left, this is something what is called the data value, like data science value pyramid. And in the bottom is a prediction. And when we have a prediction, we make a decision making. From this decision making, we build the tools that involve this decision making. These tools affect the strategy and ROI of the business, and then it affects some society. On each level, we have some metrics. And what we want to have some connection between the prediction and all the metrics on all of the layers of the pyramid. And on the right, there is one of the example. Actually, it's the simplest possible, and you'll have the presentations of the links to check it out. But if you know what is the cost of the mistake of the wrong prediction, and you know what is the value of your prediction, for example, what is the value? You can get to some sort of called the unit economics of the predictions. For example, if your prediction is right, maybe you save a couple of minutes of work of some person, which is basically saving a couple of dollars. But if you, for example, make a wrong prediction, this person has to actually spend time and spends much more time. So maybe you lose $10 or $20 on this misprediction. And knowing the value of correct prediction that you maybe do in 90% of the cases, and the value of the misprediction that will cost you something, basically you can estimate the returns that you're going to have from your model, just like financial returns here. And you can also actually estimate what accuracy of your model do you need to have the positive returns. And this is a bit different mental model that is not taught in universities or data science courses. But this is direct and linear connection between your accuracy metrics and the financial outcome of your machine learning model. And you can easily incorporate it to all your F1 scores, MSCs, etc., etc., etc. And this is what can help you to think about your models just like people in finance do in terms of financial outcomes. Talking about the models, in finance, people still love all these linear models because they allow really simple domain perspective model design. So basically, it's like, I want to predict the price of some asset of Apple stock. And I have my variables that might affect it. And I completely know that I might rely on the financial reports, I might rely on the public people's sentiment, I might rely on some rumors, I might rely on the expert's opinion, and I can weight these different factors equally or not equally. So basically, it's a linear model with different coefficients, and of course with some noise factor because something's not predictable. But you always want to have a better model. And what means regularization in this model? For example, one kind of regularization which you can think of L2 regularizations, like I want to have really equal risk exposure. I don't want to be exposed too much to the opinion of people on Reddit. I don't want to be exposed too much to the news. I don't want to be exposed too much to the public financial reports. I want to have kind of like equal parameters connected to each of the factors. So I'm kind of like I'm well managing my risk exposures. And this is basically what L2 regularization does. But for example, in some cases, you want to really cut off something what is not reliable. For example, statistically, maybe news is not that reliable. And you want to cut it off completely to the zero or almost to zero, just like L1 regularization does. And from this perspective, regularization makes really nice financial domain perspective sense. It's like you don't do regularization because you have to do it, because they taught you in machine learning course to do this, because it has really, really clear financial representation you can explain to the investor. Unfortunately, what happens in the data science in, so to say, real world, we do all these dropouts, L1, L2 regularization, but how do you explain a person in finance what actually dropout does to your financial investment decision? There is no way to explain it. And if you talk about actually physical modeling or chemical modeling or any other kind of modeling, these formulas, they affect model parameters based on their magnitude, for example, as an LX regularization, or based on the codependency like dropout, but it has nothing to do with the domain. There is no way to explain it as a modeling and investment decision. And there is a relatively recent trend that it's called the domain-aware regularization. For example, and actually it works pretty well with deep learning. It means that you set up the differentiable constraints not based on the parameter value, but based on some physical or domain model. For example, I am no expert, not in physics or chemistry, but these examples there are explainable very well from the kind of model design point of view. You have your favorite autoencoder to extract the features, and then based on that, over that, you have some differentiable physics model, and you want to respect some boundaries of some partial differential equation. These boundaries, they are parts of the equation that is differentiable. Why don't put it as a regularization? So your deep learning model respects the law of the physics. And this is regularization you can explain to the physical expert. In cases where you don't have a physical, chemical, biological model, there is a more flexible approach that it's called the adversarial loss or adversarial regularization. That's what, for example, done a lot in the drug discovery. You have your autoencoder or GAN, whatever you want, where you learn the embedding of some molecule. And then in the space of these embeddings, you might want to discover a new drug, right? But you want to put some constraints on this molecule. For example, molecule has to be not acting with some other kind of bacteria, or molecule has to be active in the water or something like this. You can put these chemical constraints if they're differentiable on the embedding as it is, or you can use adversarial laws when you can say, okay, I designed this molecule, but they have to be really similar to molecules with these properties. And what is the measure of the similarity when you have no formula for similarity? It's basically adversarial learning. You can train an adversarial gun that measures the similarity between the real molecules with the needed properties, your generated molecules in the same space. And this way you regularize your model, not with dropout, but with the actually domain-aware regularization. And I think we need to do it much more often. Maybe combined with the dropout, but definitely not leaving the dropout itself because it affects parameters, but it has nothing to do with the domain we work in. Getting to the metrics, we have the right inputs, we have the right financial outputs, we have a nice explainable models. Now we need to actually judge the performance of our model. And people in finance have really interesting framework. And in a couple of words, basically what they really track for is unique risk-adjusted return over some benchmark. And what is the return here? Return is basically actual return on investment. Basically, this is main thing you want to measure. But of course, this return comes with some risk. Risk can become from the volatility, from some exposures, from value at risk of the strategy, from hedging side, from the margin, whatever it is. So you kind of want to adjust your return, maybe just by dividing by the risk. So if you have nice return, but the risk is too high, you divide by it. And this way you kind of like check risk adjusted return. So you take into account the both sides. Then of course your strategy has to beat some benchmark, because why you want to have some super fancy deep learning crypto strategy if it works worse than just investing in the Bitcoin, right? So you always compare your risk adjusted performance with some benchmark and have to be consistently better than the benchmark. And the last but not least, your strategy has to be unique. Because, okay, you have nice risk-adjusted return. It's better than the benchmark, but it's performing like 100 of other similar instruments on the market. Why do you need to even work on the strategy if you just can invest on another instrument? Because they're so correlated anyway. So in finance, this is what you're looking for. Something that is unique, decorrelated to everything else, better than the benchmark, and with a sweet point between return and the risk. But when we do our modeling, even this financial kind of modeling with normal data science, we just have, okay, accuracy and some financial outcome from the accuracy. And I think that in the regular data science, it's really hard to have the same framework. I'm still looking for it. I'm researching this area right now. But for example, some primitive rules that they have based on this framework are that when you have your accuracy surrogate, F1 score, MSC, etc., you definitely need to connect it with the economics of the prediction. So it's actually a return. The risks from the models are different. For example, lately we have many adversarial attacks. So it's like we can attack our computer vision models so they do some mispredictions. We can use this as a measure of the risk. We can use the value of misprediction, but this is really tricky and depends on the domain. So in different domains, you have different risks. You definitely need the benchmark. I know some people are doing data like modeling without benchmarking, but benchmark can be human baseline, basically how human performs. It can be some rule-based system, can be mathematical model, and you always need to compare to some benchmark, and you have to be consistently better than a person, than some rule-based, or than some other mathematical model. And talking about decorrelation, there is a fair point that we need to build ensembles of the expert models to perform better. But what I see happening a lot in the practice, people are taking the same data set, training gradient boosting, CAD boosting neural network, logistic regression on the same data with the same labels and calling it the ensemble. But basically, these predictions are 90% correlated. So basically, maybe your accuracy is 1% higher, but you're not really stacking unique knowledge. You're just making 4 very correlated model working together and even not really helping each other. So that's why when you build the ensemble of the expert models, you really need to keep track that they are decorrelated. And this is what not always happens in the practice. Okay, we talked a bit about the inputs. that inputs that they are not always staying the same. And I think it's a fair point. We see it both in the finance and in the real world. And if you think that we don't have a data set, but we have the environment, and from this continuously changing environment, maybe changing a lot, maybe changing a little, we are sampling our data, it really kind of changes the perspective for your modeling and reading the data. Then we have the outputs, and the outputs, when we connect them to the unit economics of a single prediction, our F1 score can be, for example, weighted by the economics. And this will really change your scikit-learn report. And this will really change your confusion matrix when you multiply it by your actual returns. And it's interesting exercise to do. Then you have your model. And again, this is maybe a bit doubtful point, but since we all live in the era of the deep learning, and there are so many ways to regularize deep learning with dropouts and similar things, the emerging approaches with especially in physics, chemistry, and finance, when you regularize based on the domain knowledge, I think this is the trend that will be only growing. And I hope it will move the efforts of the researchers from another way to decorrelate some connections between the neural network ways, basically to do something useful for the domain. And the metrics. So after we have the right model, right inputs, right outputs, we need to judge it correctly. And I think here the benchmark and some sort of this kind of risk-adjusted accuracy is really crucial. Now I want to come to the 2 points that are maybe, I don't want to say more complicated. They may be a bit less relatable to the regular data science, at least not in all the domains. But I think it's really nice to at least to know about alternative approaches. And in some fields, especially like physics, biology, I know a bit more about this because my company, we work in the biology and physics, first of all, and we do modeling there. And in physics, in modeling something with the engines, and there is something such a phase change. And if you have your data from one phase and you encounter the phase change, your model will not work there well, and you will require some interesting regularization, and that will defend from it new kind of data. And working in the biology, especially in the drug discovery, you want to enforce your molecules to have some particular chemical properties and to be connected or not connected to other molecules. And this is also, you cannot achieve this property with dropout or with LN regularization. All right, but let's go to the, how do we actually test? Okay, we have the metrics, but now we need to split our data into train, test, some cross-validations to actually evaluate these metrics. And usually what we talk about is train set overfitting. And train set overfitting in finance, what it actually means. It means that your strategy can perform really well on some past data from 2010 to 2020, but it performs horrible from 2020 and ahead. And from this point of view, what you really want to have in finance, maybe you want to have a bit lower returns, like lower accuracy, but this accuracy can be at least more stable. So it's not like you, when you do the cross validation, what you want to have that it's better to have, let's say 51, let's say you have like 3 folds, like k folds, 3 folds. It's better to have 51, 52, 51 than percent of accuracy of the prediction, so you're like a bit better than the random, than 54, 45, 51, because this way you have much higher risks on the both sides. And basically that's why I'm saying the underfitting there is kind of the new black, because you don't really want to overfit, you want to even underfit a bit your training set or training sets in k-fold, but at least to have kind of much more reliable performance out of sample. And how we can measure this, what people do, they actually, when we have these folds, like let's say for now it's k-fold regularization, but we will see alternatives. We track not only different test set performance, but we also track the train set performance. Just imagine that basically like we have a vector of in-sample performances and related out-of-sample performances of different cross-validation folds. And if we plot them on the graph like this, and on the x-axis you have in samples, on the y-axis you have out of samples, we can actually measure the correlation or build the linear regression with them. And what we can see that we want to see a direct positive correlation. So basically, if you perform better in sample, you want to have better performance out of sample. That means that your model is kind of adequate. But in very many cases, you'll see that you overfit so much that when the model performs better in sample, it actually performs better out of sample on the faults. This way you'll have negative correlation. Your graph will look something like what you see on the picture. And this is really interesting test how you and approach how you can use in sample data to judge your risk of overfitting on the different faults. This is you can find this if you check this paper. I attached the link to the paper, or you just Google backtest probability, backtest overfitting probability. Of course, we also know that we can fight with overfitting using different things. For example, regularization is one way to do it. Second way is ensembling. And what's interesting that in finance, we know ensembling, and one of the most popular one that is used in Kaggle, etc., is boosting, gradient boosting, right? Because what gradient boosting does, it learns iteratively one model over each other to increase the accuracy. So basically, if you're talking about the bias variance threshold in the classical statistical learning theory, boosting really deals well with the overfitting, so it reduces the bias. But what really deals with the variance is the bagging. Because when you do the bagging, you sample different pieces of the data. In finance, meaning sampling different financial situations and aggregating the knowledge from different financial situations. And when these financial situations are not correlated, we can see on the formula on the right, and again, you can double check this formula yourself, that when these samples of data are uncorrelated, you drastically reduce your variance. And reducing the variance, it means you increasing the reliability of the model. So if your model is 51% accurate and you can basically make the Bayesian model of this 51% accurate models and aggregate them. And if these models are trained on not correlated data samples, it is much better than having a boosting model trained on the whole data set that maybe have 55% of accuracy, but the variance will be too high. And what we can think about this in terms of the normal data science. Using boosting for everything might be wrong. So when you need reliability, you really better think in terms of bagging, especially if you can basically sample from your data set, have a lot of different models. And this is a not conventional approach because Kaggle taught us that boosting wins everything, right? But it doesn't win everything, especially if what you're looking for is the reliability. And also, I hope you remember that the train set is also useful in the cross-validation process as a sanity check if you actually overfit to the backtest, to the train set. And the last thing, this is really something what I saw it only in finance. If you saw it in some other courses, it's great, or other domains. This is the test set overfitting. And the idea is, since the data in finance is really limited, okay, you have 20 years of performance of some asset. You train your model in the first 10 years or do some cross-validation, whatever you want. But then you have this last 10 years to check the performance. And that's it. And it's so easy to repeat your experiments, to tweak the model, to add new variables, to make the performance in the last 10 years looking great. And this is what is called test set overfit. So basically, it means that you do multiple experiments still on a single test set. And basically, that's what most of the financial managers, data science, they report. They report, this was my 10 years of data. Of course, it's out of sample. And here, look, my super cool strategy. But you did everything to overfit to this train set, to this test set. And how to fight with the situation? Because it's true that you actually have only one test set. And overfitting to this test set, it in a way seems natural, but it doesn't mean that it will perform the same in the next 10 years after that. There is no promise in this. In finance, there are two techniques that I have found that I think are really interesting. I will not dive into details of them because this is really domain specific, but I'll go into the kind of like gist of the main idea. What you can see on the left is called combinatorial cross-validation. So basically, instead of making like a k-fold, when you have like k groups, and you simply say, okay, I have k minus one groups for train, and the last group stays for test, and you do it iteratively. Combinatorial cross-validation tells that you can actually shuffle your dataset and shuffle in such a way that you say, okay, I have, let's say you have 10 groups, and you say, I want to have 8 groups for train, 2 groups from test, and you do all the different combinations of the 8 groups for train and 2 groups for test. And using these 8 groups, you fit your models, do the cross-validation for the modeling, and using the last 2, you do the actual backtest of the strategy. And the stay you have combination 8 by 2 of the different backtests, and it helps you to estimate basically the backtest performance much more times. And this is kind of like a nice estimate for the simulations of the data. What you can see on the right, basically this is the formula for something called deflated Sharpe ratio. And this helps you to discount your Sharpe ratio, which is kind of the performance of your strategy. It takes into account the certain four central moments, so basically skewness and kurtosis of your returns, of your Sharpe ratios from the multiple experiments. Because when you do this modeling, you have multiple experiments. You try different parameters, different models, and hopefully you store all the results of your experiments. And what most of the researchers do, they take the best one of all the experiments, they report the parameters of the best experiment and say, wow, I found the best strategy. But doesn't take into account not normality of this results, which can be represented by discounting by skewness and kurtosis, which you can see on the formula below. And also it doesn't discount for the multiple testing. And if about the cross-validation is kind of clear, but what is multiple testing? Multiple testing means that you can run many experiments, many different variables during the same time period, and there is a pretty high, not high, but not zero probability that you'll find some correlation that means no causation. It's like letters in winning word in Scripps National Spelling Bee, what it is, correlates with number of people killed by spiders. There is a correlation, and if you run experiments for long enough time, you can find this correlation, but doesn't mean that you found a good model. Doesn't mean that you found a good rule. And what is done in finance by quants, and what I think we all have to do when we experiment with the models, with the variables, with the designs, within a single data set, we should report all these experiments. Because then using some formulas for family-wise error rates or something like this, we can kind of discount our best result for the not normality of these results, or for example for this multiple experiments, and have actually much more adequate picture of what we did, instead of making 10,000 experiments, picking the best one and saying, wow, I found the model, because most probably no, you didn't. And since we have 15 minutes left, and I also think it will be great to have a discussion, if someone asks me what I want you to remember from the speech, I think it's mainly three things. What are crucial? First of all, it's not a data set; it's an environment, and I'm pretty stable opinion of mine already, and I think I can defend it with many different observations, empirical and theoretical. Second is a bit more doubtful, but at least in domains where I work, and my company works, it's biology, physics, and finance. Model like it's 100 years ago. So all the domain-related regularizations, they really rock, they work. And they do actually the heavy lifting. And you can use actually even simple linear model regularized correctly, and it will do a really good job. And third, and I think this is really important, and empirically it's correct, you should connect your machine learning metrics to the business metrics and track that. And also, I think that reliability today is much more important than the accuracy on the test set. Look to the point one. This is environment, not the data set. And if you want to discuss it anytime, just Google me, and I think you will find my LinkedIn page, and we can connect there. Basically, from my side, that's it, and maybe we can have a discussion.
Alex, thank you very much. I think we have a couple of questions in the YouTube. You want me to read them, or you want to open the page yourself? How you prefer?
Maybe you can read it, or I can check it. Wait, because I had it.
I can read it if
Please. Thank you.
it's easier for you. Okay.
Yeah.
So the first question is, can we create a deep learning model that feedbacks the previous loss at t-1? If the markets are continuously changing, can this way make it more adaptive?
I know what you're referring to. You're referring to things like active learning, online learning, maybe reinforcement learning. To be honest, I'm not expert in these things. For example, what is my approach, at least what I understand well, what I use and works, is focusing a bit more on the reliability. What you're talking about, basically, this is like reinforcement learning. Basically, you act in the environment, and if your previous action was not profitable, this is kind of your reward, and you update your model and your policy based on this reward. Or like in active learning, if your last prediction, both accuracy wise and financially wise, was bad, you retrain your model, giving kind of more weight to this bad prediction. But I never did it in practice. There are theoretical frameworks, but what I see kind of works in practice, it is what investors want to see and what our clients are okay with, if it's reliable. And then, for example, you kind of focus on the environment. So this way you still, I don't want to go too deep. I think this is the answer.
Thank you, Alex. Second question is actually my question. I wrote in the chat, which is regarding the shuffling of the data for creating the different testing folds. I'm not sure, do we need to maintain the time causality when we do those splitting between training and test? But in the framework you showed us, there's like this random shuffling, then would that invalidate this hypothesis?
Basically, you can control for the timing constraint as well, but basically the idea is kind of the same with the stochastic simulations. So, for example, when you want to do Monte Carlo simulation, you have your kind of data set. You say there is some mu, sigma, and other parameters, and you sample a lot of differential equations trajectories, right? And then you kind of backtest them all, and you have your kind of estimate of different scenarios. And here, idea is kind of the same, but when you don't know what your process is, you cannot build a differential equation for Monte Carlo. You kind of reshuffle your data set. So this way, you kind of have still the same mu, sigma, and other parameters, but kind of by reshuffling it, you have different paths, right? And the idea is that you have the same properties of stochastic process, but different realizations.
Right. But do we need to group the data into, I don't know, days, for example? Because otherwise I take random, I need to have a sequence that I cannot break the sequence. If I break the sequence, I break the pattern. So how do I slot the data?
That's the point. I think it's not necessary, especially because who said that this pattern is actually causality? Because there is no proof to this. And for example, the pattern, I mean that, that's a tricky question. But basically, if you, for example, I know what you mean, that, for example, you take some data from the future to train and test it on the past. The idea is that if they are independent, and we assume that they're actually independent, because if we, that's the kind of the most risky-less assumption. This way that the situation from the past, it actually never happened from the perspective of this future block you took. And if
Okay,
the
so
pattern,
if the data are quite far in time,
and
it
the idea
shouldn't
is
be a problem.
if the pattern you found, for example, there is a pattern even in the candles, right? Here it's true. It means that, for example, it might be true in the beginning as well, because from the cross-validation perspective, this is completely unseen piece of data. So from the cross-validation perspective, it's true. It's correct. from the financial logic and data respect perspective, if the pattern was in the past and in the future, but kind of flip them and test the correlation between the patterns. If the correlation stands, the flip doesn't change because the correlation it's doesn't mean if you change the sides.
Okay. Maybe we don't need to take points that like train and test if they're very close in time and we invert them, that might be maybe an issue. But if they are
Yeah,
quite far in time, then it shouldn't be an issue.
for this, there's actually a thing that is called basically you see embargoing and purging, but I didn't mention it on purpose because basically what you mentioned, they're called too close to time. You actually need to make cuts between the folds. Actually, the procedure when you shuffle, you make kind of like the holes between the shuffles to avoid any data leakage. But basically, it's a bit.
Okay.
Yeah.
Thank you, Alex. There are question about how about the Kalmar ratio?
If I remember right, this is divided by the value at risk or something like this. I know about Sortino, Kalmar, I don't remember. Basically, it's but the idea is the same. It's still risk-adjusted return and risk you choose for yourself. And the idea is that I really like there are so many different kind of ratios in finance because there are so many different risks. And I think we really need it in the regular modeling, like to divide our accuracies by some risks. And that's why I mentioned here. I think the choice of the Kalmar, Sortino, Sharp, whatever you want, is coming from your investors' goals. Basically, what your investors are afraid of, what's the risk, that's what you need to track. Because, for example, some investors, they track Sortino because they don't care about the drawdowns. They just want the high returns. And that's what okay for them.
So Irene replied saying the Kalmar ratio looks at the drawdown as a key of performance. The higher Kalmar ratio is better performance. I've heard many use the average of the last 3 drawdowns instead of only the largest.
Again, I think that the risk, this is something what is custom that you define with your investor. Yeah, if it is drawdown, it means that if your investor really doesn't want to see the drawdowns because it's, it's a pension fund or something like this, then you design the metric for your investor. And that's kind of like the whole idea.
Okay, let's see. Anybody wants to ask any question? You can use the chat. There you go. From the successful models that you have experienced, what is it actually predicting? A price range for stop loss or an take profit, or is it a direction in the next n hours or days? On the other hand, I think what is the target you're trying to predict, and maybe what is the loss function?
What I think the two things that worked for us really well, it's the basically this idea of kind of like barrier modeling. So basically you define basically take loss and stop profit and over the same horizon, and multitask learning. So basically you want to predict the kind of like several variables. You want to predict, okay, for example, this is good for the like active trading strategies when you want to just make a deal like inside. But for example, when you are in the world of rebalancing your portfolio, what you're actually looking for, you're looking kind of like at the end of the period when you rebalance your portfolio and want to predict how to allocate your assets, right? So there you have kind of fixed horizon, but still with next to this horizon are related some risks, for example, the same as volatility. So what you want to do, you want to predict both the change of the price from now to the next quarter, for example, and you add additional losses. Like you also want to predict the volatility, maybe you want to predict the skewness and kurtosis of the returns over the next quarter because it will help. Again, this is like one of the ideas why I talk about this because you really design what you want to predict based on what your client want, and then you connect to the financial losses because our clients they cared about what is the performance within the rebalance period, and if we can predict it and if we can allocate accordingly, right? So that's we predict not just the price change, but we predict the volatility, we predict the skewness and kurtosis, which are also some measures of the risk. And based on that, we're doing the allocation. But I cannot tell you that it improved the model by a lot. I can tell it went more stable, but we used these predictions because that's what our client needed for the allocation strategy. These two things work well.
So does that mean that you need to have a trading strategy already in mind, and
Of course.
you simulate always the same? So you're not optimizing the strategy, but you say, given that strategy, what if I deploy the strategy now? Then what would be the return? Then you just decide whether applying the strategy or not based on if the return is positive or
I
not.
would really
Something like that.
separate. I would really separate model, strategy, and risk management because they're really, really separate. And for example, when we talk about the model, the predictive value, we are coming to these points. So basically, we're talking about what are the good inputs, and the environment, especially we can see it really well. It's like in crypto markets or in the stock market. It's like the signals, predictive signals, are always changing. And when you think about the modeling, you think about, first of all, what kind of factors you have. And you need to research these factors continuously. Then you have a strategy. And when you want to predict something from these factors, you take into account your strategy, and financial losses is coming here. And it's also a separate subject. What is the strategy? How long you want to stay in the deal? What is your take profit stop loss, right? And then you also have the asset allocation, which is the risk management. And you also might want to kind of make some predictive modeling to use these predictions in your risk management. So this is kind of separate.
So there are 3 models in total. You don't optimize all of them together.
No, they're separate. Yes.
Okay. And then there is another question that is, from your experience, what is more important to reach to a stable model? Is it alt data or the modeling techniques?
Okay, if the question is about the stability is actually coming from the basically, how to say, the problem is that there's still a human bottleneck here, because when a financial expert is observing the environment, he or she is kind of checking the patterns. And basically, since the financial market's kind of like a thing that wants to be in the equilibrium, but kind of new opportunities always appearing, but then they're always disappearing. So being reliable, it means that you see some opportunity. For example, like a couple of months ago, you could have bet on the Reddit signals, right? So if it is opportunity, you parse this data, you model, and it's predictive, right? And then you go talk to your investor. What is your exposure to this factor? How won't you put too much risk on this? And some investor can say bet all on this, but then you can actually evaluate that it will be not reliable after some time. And this is simply a logic. It's not machine learning. But if investors want kind of like to diversify between different risk sources, this is actually where things like regularization is coming from. You want to have equal risk exposure to the fundamental factors, alternative data, market price, and public opinion. And basically, regularization here, this is when you kind of design your reliability in a way. So here is where you design what you want to be exposed for. Here you find it, you talk to investor, and here you kind of design how you want to be exposed.
So is this the loss function of the machine learning model?
No,
The
this is
R?
this is basically a simple. Basically, this is linear regression. Basically, we say that the return prediction is some coefficient plus other coefficient multiplied by the factor 1, factor 2, factor 3, and based on these coefficients, basically you can find which factor is more or less predictive in which moment of time, and you can, for example, cut off some factors because your investor doesn't like it, or you can
Okay.
make these factors more or less equal to each other because you want to be kind of like in a way stable. It can reduce your predictive accuracy, but you can be more stable.
I see. So the factors could be anything. Like you build machine learning models to predict factors. And can you give some examples of what are those factors?
Yeah, for example, classical factors like in finance, it's the basically how much this company earn, what is the price per earning, what are the debts of the company. This is like typical fundamental things about the company performance. Then there are market factors, for example, capitalization of this company, recent price change, volatility, volume of trades. These are the market related factors. Then there are society related factors, the Twitter sentiment, the news, the experts opinion. It also, there are like society factors. Then there are alternative factors, for example, for the Walmart or any kind of supermarket. You want to track how many people go here. And if you have from the satellite images how many cars go to the supermarket chain, you might estimate that, oh, so many people are buying things there. Maybe the supermarket is so good, I want to invest in this. This other kind of factor. So it can be anything. It can be even some like really random factor that can be alive only for a month or two, like Wall Street bets from Reddit.
Right. But how the factors will get combined when there is like a lagging effect that maybe not all the factors have a reflection on the return at the same time. So you predict the factor of, let's say, in 30 days, this is your horizon for all of the factors, but some of them have effect that are delayed. Then you put them into this linear regression, but then you should account for this lagging, right? Kind of.
Well, basically, factors you don't. I think, and okay, I'm not sure I understood correctly, but you don't predict factors. Basically, factor is what you have right now. Like right now, you know this was the previous financial report of Apple. This is the price Apple has now, and this is what people already think about Apple now. This is my numbers: F1, F2, F3, and you have historical values of F1, F2, F3, and you also have historical returns after F1, F2, F3. This is basically how you make this this data set. And knowing what is today, F1, F2, F3, you can predict RI, which is the return in 1 week. I'm not sure I answered because
Okay, so then the machine learning model is taking those factors and predicting RI.
Yeah, exactly. This is like the features. This
Okay.
F1 is
This is the feature space. Okay.
Yeah, and B is the weights of the model. Yeah, so features, weights, and just I meant here that basically you can design these weights kind of towards your investing style or your investors what your investors
What
like.
is the machine learning part then? If you already have decided all of the conditions.
Fitting the beta. So basically, you look at some sample from the environment. You decide, okay, last couple of years are really relevant, and I expect that next year kind of stay the same, right? So you take last couple of years of data. You have your F, you have your R, and you basically fit a linear regression. So you find such B using gradient descent, whatever you want, that can predict well enough the return, right, from the data set. You check the metrics, you do cross-validation, you do everything you want, but let's say the model is good. And then, for example, you see that in these 2 years, the exposure to the public opinion is too high. And you can see it because, for example, this B is 0.1 and this equals 2. And this is correct to predict the price. So basically, really, this year's public opinion drives the stock prices, and this is okay. But you know that your investors that gave you 10 billions of dollars, they're kind of conservative. And you go to them and you explain them that we can reduce the exposure to the public opinion and kind of look more to the financial reports, I don't know, but the accuracy of predictions will be less and you'll earn less. But the investors say, no, that's okay. I don't trust these hipsters on Reddit. I want to trust financial reports. And they're okay with less returns, but being less exposed to some. And this is what is kind of like, this is domain-aware investor-aware regularization. This is what I meant. Like in physics, you want your predictions to be actually to be according to the physical laws. Like in chemistry, you want your molecules to be according to the molecules laws. And here in finance, you want your model to be according to your investors' opinions or beliefs because they give you money.
Makes sense. So you fix some of those and then ask the algorithm to fit the remaining.
You impose a regularization. Basically, you say that usually you have like a lot of factors, and you can say, I want to regularize a bit for the like social related factors. I want them to be like you impose regularization on them. You retrain your model. Maybe your accuracy will be a bit less, but still it will be okay because your investors, that's what they want. That's their regularization.
Interesting. All right, let's move with the other question. We have a few more. So you mentioned to model like it's 1921. Does this mean that it's very important to be a very good investor trader and then transferring that expert knowledge into simple machine learning models?
After years of this, right, when you ask me this question, this is my face in my head right now. Especially great trading ideas like taking some data from the cryptocurrencies, train a deep learning model and try to put my money on it. This was one of the great ideas. Right now, I really believe that in finance, the computational tools are a small part. Basically, the most successful projects I have had in this field are when there is a financial expert who really knows the market, who studies the data, has some primary ideas for the strategies, and me or us company as a computational partners help to evaluate these business ideas. So there is a mind that knows the market, gives sources, potential sources of the ideas, and we help to build the strategies, check how reliable they are, to build the rules. And this was so far the best and the most successful collaborations I have had in my basically my personal experience. I cannot talk about others.
Thank you, Alex. Next question. Lately, you recommend machine learning for algorithmic trading, predictive models to extract signals from market and alternative data for systematic trading strategies with Python by Stefan Jensen. Have you implemented that knowledge in this presented research? I'm wondering if your vision of Stefan's approach to predict models.
Yeah, if you talk about the Stefan's book, I think that's what I mentioned in my video. I think his book is great to kind of like to jump with the financial field, kind of like to start doing something. But let's say like this: it's a good educational book. It will teach you a lot about the data, about the algorithms, about processing, about basically the universe of approaches. But and to be fair enough, he doesn't tell you that you need to put money on his approaches. And basically, that's the point. I wouldn't recommend to do the same. So if you're just starting to study, you should go with his book. It's the fastest way to kind of get in. But if you want to start putting money on your strategies, you need to check a bit more complicated resources like Marcos Lopez de Prado book, and I mentioned some of his slides and materials in this presentation as well. So it basically depends on what stage you are. If you're just starting and you want to know what is finance, what is financial data, how to train your first model on it, Stefan is a great material. If you have to put your money on it, you need to go beyond.
Okay. Yeah, I have this idea, if you agree with me, that if I have the secret sauce of how to make money with trading, I wouldn't write it into a book because the minute you publish it, then doesn't work anymore.
Actually, all the ideas, there is a life cycle of the trading ideas. They appear, they become profitable, and they die, and that's okay. There is no strategy that will last forever. Even but there's just like value investing, but this is even like not trading strategies, like you invest in the value, so it's a bit different thing.
Yeah. Okay, we have another two. Seems very interesting discussion tonight. So how you evaluate the importance of these features? Is boosting weak learners adequate for this kind of business problem?
Yeah, basically for feature importance, what you want to do, and again, I didn't invent it, and basically this is again from Marcos Lopez de Prada. I really rely a lot on his approaches, and they don't let me down so far. Basically, you can use all your favorite feature importance models, sharp values, whatever you want, but you need to calculate them on the cross validation. or on the simulations. And this way, basically, you'll have not a point estimate of the feature importance, but kind of like a distribution of feature importances for different folds. And this way you can kind of have a much better picture. This way you can divide the mean feature importance by the standard deviation of feature importances, because, for example, on a one test set, one feature can be super important. You're like, wow, this is the alpha, this is the factor. But actually it can be just a lucky part. And on all other simulations or folds, it can be not important at all. And you need to account for that, of course. But I think whatever method you will use, it should be just fine, even just permutations.
Thank you, Alex. And the last question is, how do you take the predictions and actually create trading strategies?
Yeah, basically that's the point. It's like you need to design your predictions to be automatically fit to your trading strategy. So for example, this is also like a mistake that happens in all data sciences. Like you train a model for some objective and then you're thinking, how do I connect this objective to the actual task? It's like you train model for face recognition, but at the end you need to do something else, or okay, whatever. Yeah, if you talk about the finance, the idea is that imagine this yellow part is your X, this is your input, already correct, etc. And your output has to be connected to your investment decision. So for example, if you're looking for some like momentum opportunities, right? So basically, you know that you're looking for momentum in some condition. And what happens next? You know that you want to enter in this deal for not longer than 7 days. Your take profit is you want to have 5% and quit, leave. You want to lose not more than 1%. This is your stop loss. And this is how you create your data set. And when you create your data set with this all this kind of constraints of your investment decision, basically your prediction is already the investment decision. And even from the probability of your predictive model, you can even calibrate how much money you want to put on it. So the trick is simple. You just design your outputs to be already like decisions and be connected to the financial outcomes, both in face recognition or spam prediction or some chatbot where you automate the response, and both in the finance as well.
Should you predict the return, or it could be also like a binary classifier saying whether the strategy was successful or not?
It can be binary. I think it's okay since basically in this case, for example, it's binary because you check, are you going to hit the 1, it hits the take profit, 0, it hits stop loss. So it's binary. And you say it, if it tells you 0.3, you know that there is like a 0.3 probability to hit 1, which means 70% probability to hit -1.
All right. So that's a lot of options. Let's see. Maybe there was actually new questions as well. Of course, books for predicting of models are not a Bible to make. Too risky, and it wouldn't be published. Thanks so much for your session. Always great outputs. So I think all of the other comments are about thanking you for this amazing knowledge that you share with us tonight.
Thanks to everyone for coming, and hopefully it was useful. I mean, I tried to kind of make some connections.
Indeed, it was very, very useful. I think this from my feedback, but also reading the comments, I can clearly see there was a lot of interest.
Thank you, guys.
Thank you, Alex. And yeah, the recording is on YouTube. You will be able to watch it offline, and I guess Alex will also share with us the slides.
Of course,
so we may publish in our slides share. So check our website in a few days. You will also find the summary article published in our Medium blog.